Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to go over antiderivatives, otherwise known as the integral. Now, there's some basic antiderivative rules, just as there are some basic derivative rules. But before we jump into that, let's really go over what is an antiderivative. Well, think about starting with a derivative and trying to define your original function. How do we get back to that? We would integrate it. Take the antiderivative of the derivative, reverse the process to get back to the original function. So, for example, if I had f prime of x to start with, in order to get to f of x, I would integrate, that's the integral symbol, almost like an elongated s, and then we say what we're integrating with respect to, so dx. So if I integrated f prime of x, that would get me back to my original function. However, it might not be necessarily my exact original function because we have to think about when we take the derivative, what gives us 0? If we take the derivative of a constant, we get 0. So if we're integrating the derivative, did we have potentially a 0 in there somewhere that we didn't know? It's kind of hard to say. So if we integrate 0, we're going to get some constant. We don't know what that constant is, so we would say plus c. So anytime we have this integral, you're going to have plus c with it unless I put bounds on the integral, which we'll get into in a later example video. But bounds essentially means that I'll have some number to some other number along my integral. However, when I don't have those bounds, I need that plus c. Now think about it. What happens when we take the derivative d dx of some function f of x plus c? What does that go to? Well, c is a constant that goes to 0. Taking the derivative of f of x goes to f prime of x. And there we go. That was what was inside of our integral. So essentially, taking the antiderivative is reversing the derivative. Another way to note this is that f prime of x equals little f of x. The derivative of our antiderivative, big F, equals f of x. Now, not only can we reverse the process of taking a derivative, but if we start with our original function, f of x, and integrate that to get big f of x, or the capital letter F of x, that gives us helpful information about the function itself. Where the derivative gave us the slopes of the tangent line, when we integrate, we're going to learn about how that relates to area. But first, let's go over some basic rules, and we're going to take a look at the integral to dx. And this is just going to reinforce the concept of that plus c. So think about integrating 2 dx. Let's think about this 2 as a derivative of some original function. So if we're integrating the derivative, what would have given us a derivative of 2? Well, that would have been if we took the derivative of 2x. So integrating 2, we're going to get 2x. And you can see when we take that derivative, we do indeed get 2. But however, remember that concept of plus c? When we integrate 2, we didn't know if we could potentially have some 0 involved in there. So this is going to be 2x plus c. And when we take the derivative of this, 2x goes to 2, and any constant c, any real number, I don't know what it is, I just am using c to represent some constant, taking the derivative of that goes to 0. 2 plus 0 is still just 2. That's why for these indefinite integrals, integrals without bounds, we need to have plus c. And again, later we'll learn about those bounds that will go where I just drew those red circles. They can represent either numbers or variables, and then we won't need to include the plus c, but for now we do. But let's jump into those rules. The first rule we're going to go over is the power rule, and this is the power rule for integration. Remember, the power rule for differentiation, we brought the power down, so we brought that exponent down in front, and then we decreased that exponent by 1. For integration, if we're integrating x to the p with respect to x, we're going to essentially kind of do the opposite. So think about that ordering again. We brought the exponent down in front when we took the derivative, and then we decreased it by 1. So we're going to do the reverse. We're going to start by increasing the exponent by 1, and then as opposed to multiplying, we're going to divide. So this becomes x to the p plus 1 all over the new exponent of p plus 1 plus c. And again, we have to have this plus c because we do not have bounds on our integral. And in the rest of this worksheet, I don't have any bounds. We're going to learn about bounds or a definite integral in a later example video. So for now, don't forget that plus c. So x to the p plus 1 over p plus 1. And think about this. What happens if you take the derivative of this new function? We should get our x to the p. So think about it. If we took the derivative of x to the p plus 1 over p plus 1, pull that constant out in front, 1 over p plus 1, and then we multiply that by bringing the exponent down, that would be p plus 1, and then decreasing that exponent by 1, x to the p plus 1 minus 1, and then taking the derivative of c, that's a constant, that goes to 0. So taking a look at this, what happens? P plus 1 in front cancels out with 1 over p plus 1, and x to the p plus 1 minus 1, 1 cancels out with negative 1 to give us just that original x to the p. So there's a quick general format showing you how you can double check with the derivative. Let's do it now with our example x squared. So x squared goes to x to the 2 plus 1 over 2 plus 1, and don't forget that plus c. So this is equal to x cubed over 3 plus c. That's our solution for integrating x squared with respect to x. Now, do a quick double check, especially when you're still getting used to taking the antiderivative, and I tend to do it a lot of times just in my head. Take the derivative of your solution to double check. So when we take the derivative of x cubed over 3 plus c, we should get x squared. If we do, we know that we're correct. So taking that derivative quickly, x cubed over 3 becomes 3x squared over 3, leaving that 3 where it is because that's like the constant multiple rule for differentiation, and the derivative of c is 0. Notice my 3's cancel out to leave me with x squared plus 0, x squared. There we go, this one checks out. Let's move on to the constant multiple rule for integration. Now the constant multiple rule for integration is going to be the integral of some constant times our function, which, so I don't confuse you with a c, I'm going to make this constant a. So a, I'm going to make a note, is in the real numbers. So if I take the integral of a, some constant, multiplied by f of x with respect to x, if I'm integrating that function, a times f of x, then I can leave my constant of a out in front and then just integrate f of x dx. So I'll multiply a by that integral. Showing how this works in an example, you can see it's pretty similar to how we did the constant multiple rule for differentiation. I'll pull this 3 right on out in front and then integrate x squared dx, which we've already done x squared dx up above. So I'm going to have 3 times, what's the integral of x squared with respect to x? That was x cubed over 3, and then we had plus c. Now when I pull this 3 out in front, I don't need to multiply it to my c as well, because multiplying 3 by c is still going to give me some arbitrary constant I don't know. So we'll still just leave this as c. No need to distribute this 3 through to the c. However, if there was another term when we pulled out the 3 in front, we would need to distribute it to that. But for the sake of this arbitrary constant, it's just c. Simplifying this down, notice that my 3 cancels out with my 3 to leave me with x cubed plus c. So that's my solution. Quickly take the derivative. The derivative of x cubed is 3x squared, derivative of c goes to 0. And the last basic rule we're going to learn in this worksheet is the sum rule. So the sum rule is, again, similar to differentiation, except for this case, we're going to be doing it for antidifferentiation, or integrating. So if I take the integral of f of x plus g of x, so I have some function f of x plus some function g of x, and I'm integrating that, that's the same as splitting that integral up because there's addition in between. So I'll have the integral of f of x dx plus the integral of g of x dx. And this also works with subtraction because you can think of subtraction as adding the negative. However, unlike when we did differentiation where we learned about the product rule and the quotient rule, we're not going to be learning about these for integration at the moment. We need to use different methods for figuring out integrals where we have products of functions and quotients of functions. So these are 3 basic rules. Let's finish out this example for the sum rule. Again, I can split this up. So I'm going to have the integral of 3x squared dx, and I'm going to add that to the integral of 5x dx. Lucky enough for us, we've already evaluated 3x squared with respect to x. That was right up above. That was x cubed plus some constant c, and then integrating 5x. Remember, we can leave that constant out in front, and integrating x, power rule here, that will become x to the 1 plus 1, because this is like x to the 1. So we're going to increase that exponent by 1 and then divide by that new exponent. So divide by 1 plus 1, and this also has a plus c. However, because we have plus c and plus c, remember, it's just some arbitrary constant, so I don't need to take into account 2 different constants. I'll group them together as one individual c. So I'll go ahead and erase this one for now to leave me with just 1 plus c. Simplifying the rest of this down, I'll get x cubed plus 5x squared over 2 plus c. Double check with the derivative since we're still learning. X cubed goes to 3x squared, 5x squared over 2. When I bring that 2 down in front and decrease the exponent by 1, that 2 will get canceled out with the 2 in the denominator to leave me with 5x. So let's do 2 quick examples now that we've learned these 3 basic rules of integration. Well, in part A, we have subtraction in between, so we're going to start by using the sum rule. So I'm going to split this up into the integral of 2x to the 4th dx, and I'm going to subtract the integral of x cubed dx. Integrating 2x to the 4th dx, I can pull the 2 out in front and simply integrate x to the 4th dx, and there's nothing to pull out in front, no constant multiple rule to manipulate here, so I'll leave this as the integral of x cubed dx. Now let's go ahead and evaluate each. Integrating x to the 4th, leaving that 2 out in front, x to the 4th goes to x to the 4 plus 1, which gives me 5, all over that new exponent, 5. And then I'll have some plus c. However, because I have another integral here, I know I'm going to get a plus c for that as well, so I'm just going to put my plus c over here, so I don't forget about it. Now I'm going to subtract the integral of x cubed, so increasing that exponent by 1, 3 goes to 4, and then dividing by that new exponent of 4. So writing this all together, this will be 2x to the 5th over 5 minus x to the 4th over 4 plus c. Do a quick double check. If I bring that 5 down in front when I take the derivative, that then becomes a 4, so I'll have 5 times 2 over 5 times x to the 4th, which is 2x to the 4th, and then when I subtract x to the 4th over 4, dropping that 4 down in front and decreasing that exponent by 1, I do indeed get x cubed. There we have it. That is the integral in part A. Now, in part B, we have the integral of pi r squared plus 2 pi r, all with respect to r. So even though we're integrating with respect to a different variable, the same methods still apply. Our function is in terms of r, and we're integrating with respect to r. So here we go. We're going to split it up first by doing the integral of pi r squared with respect to r, and then we're going to do the integral of 2 pi r with respect to r. Notice that I have a constant of pi in my first integral, so I'll pull that out in front and then integrate r squared with respect to r. And then in my second integral, I have a constant of 2 pi. So I'm going to pull that 2 pi out in front and then integrate r with respect to r. So here we go. Pi will get multiplied by the integral of r squared becomes r to the 2 plus 1 over 2 plus 1. So r cubed over 3. And then we have that plus c, which I'll put all the way over here since this integral also has a plus c. And then I'm going to add that too, leaving my constant of 2 pi out in front, integrating r, increasing that exponent of 1 by 1 becomes r squared all over 2. And simplifying down a bit, this 2 will cancel out with the 2 in my denominator. So I'm going to have, as my final solution, pi r cubed all over 3 plus pi r squared all plus c. Now we're going to talk about the antiderivative for functions dealing with e and the natural log. How do we get something involving e with an antiderivative, and how do we get something with a natural log? Well, let's think about it. If we integrate e to the x, that's going to be e to the x plus c, because the derivative is itself. So if we take the derivative of this, the derivative of e to the x gives us that e to the x, and then the derivative of c goes to 0. So the integral of e to the x is e to the x plus c. Now remember up above, I said our power rule works as long as our exponent isn't a negative 1. Because if it is the negative 1, we get 1 over x. But think back to differentiation. When we took the derivative of something, we got 1 over x, and that was the natural log. So integrating 1 over x gives us the ln of the absolute value of x plus c. And we need to make sure we have the absolute value of x in here, because remember the domain of the ln function, that's for numbers that are greater than 0. So let's move on and do a couple quick examples. We're going to integrate the following functions, starting with a. Well, for a, we're going to use a little bit of the constant multiple rule. We're integrating with respect to t, but I can pull that 7 out in front since 7 is multiplied by everything in my integral. So then I'll just integrate e to the t dt. Remember, e to the t dt when integrated is e to the t plus c. So this is going to be 7 times e to the t plus c, and again, 7 times c, it's still just some arbitrary constant c, so no need to distribute that through. So this will just be 7e to the t plus c. Now, on to b. Remember how I said up above that we don't really have any method for doing the quotient rule or the product rule with integration, because integrating, even though some rules are similar, they're not all the same. So we can't do the quotient rule, so the only way we're going to be able to integrate this is hope that it simplifies down into something we can integrate with those 3 rules we know. So if I have x squared plus 5 over x as my function, well, I can split this fraction up because I already have that common denominator of x. So this is going to become the integral of x squared over x plus 5 over x dx. And what does that give me? That's going to be the integral of, well, x squared over x is just x dx plus the integral of 5 over x dx. So you can see there, I simplified this first fraction down and used the sum rule. Now I'm ready to integrate. The integral of x goes to x squared over 2, and the integral of 5 over x constant multiple rule, pull that 5 out in front. What's the integral of 1 over x? ln of x. So 5 ln of the absolute value of x, and this is all plus c. And don't forget to double check by taking the derivative. Now, let's move on. In part C, if we were taking the derivative, we might use the product rule. However, we're not. The same rules don't apply, so we cannot do this unless we can simplify it down. And think about this, y to the negative 1, we can write in the denominator as y to the positive 1. And then I'll be able to split my fraction just like before. So this is going to be the integral of 4 over y plus the square root of y, I'll write as y to the 1/2 over y dy. Simplifying this down and splitting the integral up because of the sum rule, 4 over y, I'll integrate that with respect to y, and then y to the 1/2 over y, that becomes y to the negative 1/2 dy. Now, constant multiple rule, bring that 4 out in front. What's the integral of 1 over y? That's going to be the ln of the absolute value of y. So this is going to be 4 times the ln of the absolute value of y plus c, but I'll leave my c for the end. How do I integrate y to the negative 1/2? Well, that becomes y to the negative 1/2 plus 1 all over negative 1/2 plus 1. And this is all plus c. Let's go ahead and simplify this down. I'll get 4 ln of the absolute value of y plus negative 1/2 plus 1 is going to give me a positive 1/2. Y to the positive 1/2 is going to be the square root of y. And I'm dividing by negative 1/2 plus 1/2, so dividing by a positive 1/2. But think about dividing by a fraction. That's the same as multiplying by its reciprocal. So this is going to be 2 times the square root of y, and then plus c. Now this one, especially since we haven't worked with fractional exponents, is going to be a great one to double check with the derivative. So do that now before continuing on. Now that you've done that, moving on to part D. Hopefully we can rewrite this in order to integrate it. Let's see. Well, first of all, I can pull the 1/3 out in front. And then also, this e to the negative exponent can be flipped and written as a positive. So this is really 1/3 e to the positive x dx. E to the x is e to the x. So this is equal to 1/3 e to the x plus c. E to the x over 3 plus c. Now let's talk about the antiderivative for trig and inverse trig functions. So if you need to, reference that original worksheet we did when taking the derivative of trig functions and the other worksheet when we took the derivative of inverse trig functions. So what we want to ask ourselves is taking the derivative of what gives us what's inside our integral. So let's zoom on in. Taking the derivative of what gives us cosine of x. The derivative of sine of x is cosine of x. So the antiderivative of cosine of x is sine of x plus c. Scrolling on over, so if we're taking the integral of negative sine of x, remember taking the derivative of cosine of x gave us negative sine of x. So this is going to be the cosine of x plus c. But let me ask you this, because it's going to come up in our examples and I want to prepare you. What happens if this was integrating a positive sine of x? How do we take the derivative and get a positive sine of x? That would be taking the derivative of a negative cosine of x. So when dealing with sine and cosine, cosecants and cotangents, remember that the negative does indeed matter. But just refer back to your derivatives if you need help taking antiderivatives. So moving right along, what is the integral of secant squared of x? because we don't know what the integral of just secant of x is, because we didn't have a derivative of a trig function that just gave us secant. But what trig function, when we took the derivative of it, gave us secant squared of x? That was the tangent of x. So this becomes tangent of x plus c when we go to integrate. Integral of secant squared of x dx is the tangent of x plus c. And again, for negative cosecant squared of x, that becomes a cotangent of x plus c. Taking the derivative of cotangent of x, we get a negative cosecant squared of x. So again, if this was positive, then this would become negative when integrating. So again, keep track of those signs. And then lastly, like I said, we don't know how to deal with the product rule. However, remember what derivative gives us secant of x, tangent of x. That was the derivative of secant of x. That derivative was secant of x, tangent of x. So when we integrate secant of x, tangent of x, we can do that, but don't forget our plus c. Same with negative cosecant of x, cotangent of x. That was the derivative of cosecant of x, but when we're integrating that, we can't forget our plus c. So those are our basic trig functions. Now let's take a look below. Here we have three basic functions when integrated are going to give us inverse trig functions. So the integral of 1 over the square root of 1 x squared is going to give us the inverse sine of x plus c. The integral of 1 over 1 plus x squared is going to give us the inverse tangent of x plus c. And then the integral of 1 over x times the square root of x squared minus 1, that's going to be the inverse secant of the absolute value of x plus c, making sure we remember that domain. So now that we've gone over the basic trig, let's go ahead and do these quick 6 parts of example 3 using all the different strategies we learned on this worksheet. Our 3 different rules: power rule, constant multiple rule, and sum rule for integration, and our basic integrals. So zooming on in, we first have 3 times secant of x all multiplied by secant of x plus tangent of x dx. And I used brackets just to show you that we're taking the integral of that entire thing. But we don't really know how to integrate it without attempting to simplify it down first, so let's see if we get somewhere. I'll do the integral of, I'll go ahead and distribute this 3 secant of x in, or actually better yet, I'll pull this 3 out in front so I don't have to worry about it. So pulling the 3 all the way out in front, now we'll just distribute secant of x to secant of x and tangent of x. So I'll get secant of x times secant of x, which will be secant of x squared, plus secant of x times tangent of x. Can I integrate each of these? Yeah, I totally can, because they were actually definitions from up above. But remember, this 3 is out in front and it's multiplied to absolutely everything. So I'll have 3 times the integral of secant squared of x dx plus the integral of secant of x times tangent of x dx. So integrating secant squared of x, that becomes, well, what's the derivative that gives us secant squared of x? That's tangent of x. So that becomes tangent of x. And then what does secant of x, tangent of x, when we integrate that, that gives us secant of x, because the derivative of secant of x is secant of x times tangent of x. And remember, this is all multiplied by 3. And what can we not forget? We cannot forget our plus c. So 3 times tangent of x plus secant of x plus c. Moving on to part B, we have 5 cosecant of x, cotangent of x. Pull that 5 right on out in front, and what do we get? What's the integral of cosecant of x, cotangent of x? Well, the integral of negative cosecant of x, cotangent of x is a positive cosecant of x. So the integral of a positive cosecant of x cotangent of x is going to be a negative cosecant of x. So this is going to be equal to a negative 5 cosecant of x plus c. Let's do a quick double check. What happens if we were to take the derivative with respect to x? Well, the derivative, leaving that negative 5 out in front, the derivative of cosecant of x is negative cosecant of x times cotangent of x. Negative times negative gives us a positive, so that would be a positive 5 cosecant of x cotangent of x. Derivative of c is just going to be 0. So this does check out. So our solution is negative 5 cosecant of x plus c. Let's continue on to part c. In part c, we're integrating with respect to t. And this 8, constant multiple rule, we can pull that 8 right on out in front. And what do we have? We have a 1. So this is going to be equal to 8 times the integral of 1 over the square root of 1 minus t squared, all with respect to t. How do we integrate this? That's the inverse sine. So this becomes 8 times the inverse sine of t plus c. Moving on to part d, we're going to be integrating with respect to r. So r squared over 3 plus sine of r dr. We can split this integral up using the sum rule. R squared over 3 dr plus the integral of sine of r dr. And the more comfortable you get doing some of this in your head, you won't have to split it up and write out all your work. You can just integrate each of those individually without showing the sum rule. But because I already have it written out, I'll just go ahead and leave it. So integrating r squared over 3, that's 1/3 times the integral of r squared, which goes to r cubed over 3. And then integrating sine of r, if we have a positive sine of r, what trig function of r gives us a positive sign as the derivative? That's going to be a negative cosine of r. So integrating sine of r is a negative cosine of r, and we can't forget our plus c. Simplifying this down, we'll get r cubed all over 9 minus cosine of r plus c as our integral in part d. And if you want to double check, let's take the derivative of this. Bringing that 3 down in front and decreasing it by 1, we'll get 1/3 r squared, which is r squared over 3. So that first integral checks out. And then double checking, taking the derivative of cosine of r is going to be a negative sign, minus the negative sign is plus the sine of r. So that is correct as well. Let's move on to E, our second to last example problem. 10 over 5 plus 5y squared. This looks a little difficult, but, well, first we're integrating with respect to y, and we have some common terms we can pull out. For example, we can pull this 10 out in front, and then we'll be left with 1 over 5 plus 5y squared. But what else does the denominator have in common with each of those terms? A 5. So not only is it 5 plus 5y squared, but it's 5 times 1 plus y squared. Pulling 5 out of each of those terms, if I distributed it back in, we would indeed get 5 plus 5y squared. But this is nice because now I can pull this 5 all the way out in front as well. So simplifying this completely down, it's going to be easier to see how to integrate it. We're going to be integrating 10/5 times 1 over 1 plus y squared with respect to y. This is essentially that formula from up above for inverse tangent function. So this is going to be equal to 10/5 times the inverse tangent of y plus c. And what does 10/5 simplify down to? Let's make this a little neater. 10 over 5 is 2. So this is 2 times the inverse tangent of y plus c. And lastly, part F. We have this 7 times x to the negative 1 times the quantity x squared minus 1 to the negative 1/2. Let's move those exponents down into the denominator so that they're positive and see if we can then figure out how to integrate it. So we're going to have the integral of e to the x plus 7 remains in our numerator, or I can leave this 7 out in front, times 1 all over x times the square root of x squared minus 1. We're going to be integrating this all with respect to x. And look, do we know how to integrate e to the x? Yes, we do. Do we know how to integrate 1 over x times the square root of x squared minus 1? Yes, we do. And with that 7 out in front, it's just the constant multiple rule. So let's go ahead and integrate each of these parts all together now. The integral of e to the x is e to the x plus, pulling that 7 out in front, the integral of 1 over x times the square root of x squared minus 1. Remembering our formula, that is the inverse secant of the absolute value of x. So the inverse secant of the absolute value of x, and can't forget our plus c. And there we have it, our final solution on this example worksheet. Now, with our current knowledge for integration, we only have a select set of rules and a select set of methods to go off of. So using those known techniques and a little bit of algebra, we can already integrate a lot of different problems. Eventually, we're going to learn a new integration technique and then even more integration techniques when we get into calculus 2. But I would say the best thing you can work on in order to succeed is to make sure you know how to take derivatives, because you can always double check by taking the derivative of your solution once you integrate and see if it's correct. So I would definitely practice derivatives before continuing on, and then also practice these basic integrals. So let's go ahead on to the next video where we'll learn a little bit more about exactly what an integral is. But until then, continue to practice and good luck with your online learning.